Hey, Calculus 2 students. Welcome to this extra example video on computing the volume of a solid. Our strategy that we are using in this course to compute volumes of solids via integration is by slicing the solids. So we slice them up into thin slabs, compute the volumes of those little slabs, and then add up to get the total volumes. Now, with some solids, there's really only one way that you can slice them. For instance, with a solid of revolution, you're going to want to slice it perpendicular to the axis of revolution. For other solids, there's some more variety, and I want to show you an example like that here, where we have a solid that actually we can slice in 3 different directions, and the computation will look different each time, but hopefully, of course, the volume of the solid is still what it always was. We should get the same answer any way we slice it. So let's take a look here. So here's our solid. You can see that it is a wedge. And truth be told, we could compute the volume of this solid without using integration at all, thanks to some basic formula from geometry. But let's do it with integration just for a fairly simple example with some extra practice here. So you'll notice that first we want to calculate the volume by slicing perpendicular to the x-axis. So you can see the x-axis here kind of coming out of the screen to some extent and a little bit to the right perhaps. Okay, so if we slice perpendicular to the x-axis, one of our slices is going to look kind of like this. Let's see if I can get that. There it comes. Okay, so a slice or a cross-section, we'll have part here that we can't really see, so we'll draw that with a dotted line to some extent. Okay, yeah, I might as well just fill it in. Of course, we wouldn't be able to see part of that slice if we didn't have X-ray vision. Okay, so what you can see here is that the slice perpendicular to the x-axis is going to give us a rectangle. So let's draw that rectangle over here in such a way just that we can see it and work with it more easily. So we will get rectangles that look like this. And we'd like to know the dimensions of that rectangle. Well, one dimension is very easy, and that is that this dimension in the y direction, we can see that that is 4. And as you imagine slicing this wedge in different places, you can see that the height of the rectangle is going to change. You know, a slice over here is going to be a very short slice. Oh, it's kind of disappeared. Okay, whereas the slices toward the back are definitely going to be taller slices. But the width always stays the same. The width is 4. Now the height of our slices this time, we can see that those are they're vertical, so they're going to be measured along the z-axis. And so what we'd like to do is express z in terms of x, because we are going to be integrating with respect to x here. We're dividing up the x-axis into little subintervals, which will have width dx, and the dx then will be the thickness of our slabs. Okay, so what is z in terms of x? Well, here we can do some analytic geometry to figure that out. For this purpose, we really just need the x-axis and the z-axis. So let me get another diagram going here where we can just focus on those. So there's x and z. You can see where that would be in our 3-dimensional coordinate system as well. But just focusing on these 2 dimensions, so we see that the top of the wedge here is represented by a line that looks like so. And that is the line that goes through the point 0, 2 and the point 6, 0. Let's see if I can put in some hash marks here that make it hopefully clear. Okay, that's a point 6, 0. So those are 2 points on this line. Now, the reason that this line is important is that at any given slice, the height of it is going to be the height of our rectangle is going to have its top on that line. Its bottom will just be on the x-axis. So we want to figure out the length of that line segment. Well, the length of that line segment is just going to be the y or the z coordinate of that particular point. Okay, so we can find that. We can express z in terms of x by giving an equation for this line. So there's our analytic geometry for this approach. Well, to find the equation of the line, first of all, we need the slope. And we know that the slope is going to be rise over run, so we could do 0 minus 2 over 6 minus 0, which is negative 2 over 6, or negative 1 over 3 is another way to express it. Okay, so the slope of that line is negative 1/3. And we actually have the z-intercept. We got the intercept here, and it is at 2. And so we can go straight to slope-intercept form and say that this line has equation z equals mx plus b, so that's negative 1/3 x, and our y-intercept is here at 2. Whoops. Keep wanting to call it a y-intercept, but in this case, of course, it is z. Okay. So there we go. This is really what we wanted to get is the height of our rectangle. And so we can get the area of our rectangle now, and that'll quickly lead us to our differential of volume. So the area of this particular cross-section is going to be 4 times z, or in other words, 4 times negative 1/3 x plus 2. Okay, and then our differential of volume. So for volume here, we are doing a differential because we have these very thin slabs with this thickness of dx. You get a dx in here, it would look, again, something kind of like this. Okay, and so there's one of our slabs. Very thin, just with the our thickness of dx. So then our differential volume, especially if we distribute this 4 here, which we can do, we'll have negative 4/3 x plus 8. Oh, that's the area, and then multiplied by the thickness, dx, gives us our differential volume. Now we got to add up all our differentials of volumes, and of course we do that with an integral. And in this case, if we look at where our slabs are going to be, they're going to span all the way from 0 to 6 along the x-axis. So here we get that the volume itself is going to be the integral from 0 to 6 of negative 4/3 x plus 8 dx. That's a minus there. Didn't make it look too much like that, but okay. So now we just need to evaluate this integral. And again, this is more than half the battle, getting this set up. So when we anti-differentiate here, we're going to have negative 2/3 x squared plus 8x. And then we want to evaluate this at 0 and 6. Okay, putting 6 in there, we'll get 36 times negative 2/3. And, plus 8 times 6. Okay, evaluating at 0, as it tends to do a number of times, is going to give us 0, so we subtract 0. Okay, and then we just need to finish this off with some arithmetic. Negative 2 times 12 would be negative 24. And 8 times 6 is 48. And add those together, we get 24. Okay, so the volume of this wedge, not a huge surprise here, but it turns out to be 24, and this time we obtained it by slicing perpendicular to the x-axis. Okay, now what would happen if instead we slice perpendicular to the y-axis? Again, you can't always expect you're going to be able to slice it any which way, but this time it's going to work out. So imagine slicing perpendicular to the y-axis and see what those slices are going to look like. And then we'll take a look at it on the next slide here. There it is. Okay, perpendicular to the y-axis now. What type of shape are we going to get for our slices? This time they are going to be triangles. So at this particular y value, we get a triangle that looks like that. Probably be good if I could draw straight lines better. Easier said than done. Okay, so let's draw one of those triangles over here. And interesting thing with this solid, okay, and these are right triangles. With this particular way of slicing, the slices actually do not change, right? All of the slices are going to be triangles, and not only that, but they are all going to have that same base of 6 and the same height of 2. Okay, so in this case, the area of one of our cross sections, slice, is just going to be 1/2 base times height, and so that is 6. So they all have area 6, which means that our differential of volume is simply going to be the area of the cross section times our thickness, which is just dy. We're carving up our y interval here with small subintervals of length dy. And then we just need to add up the volumes of all those slabs. And here along the y-axis, we go from 0 to 4 with that. That's the extent of our solid in that dimension. And so the volume overall is just going to be the integral from 0 to 4 of 6 dy. Okay. This is an especially easy integral. Maybe falls into the so easy it's hard category, but in any case, antiderivative, if you want to do it this way, is just going to be 6y. And evaluating that at 0 and 4, we get 6 times 4 minus 6 times 0 is just going to be 0. And so once again, we get 24. Same result as before, so very consistent. That's good. If you had to pick just one way to do this integral and you wanted to make it an easy one, this is probably the easiest way to slice it. But let's go ahead and see what happens when we slice perpendicular to the z-axis as well, just to see how that looks and how that turns out. Okay, so here we go to that. Here's our third situation, slicing perpendicular to the z-axis, and see if you can picture what type of slices we're going to get this time. Well, once again, although they look kind of different thanks to their orientation, but once again, we are going to get rectangles from this. This time they're horizontal rectangles like so. And we're slicing at some particular z here. And we're dividing up our portion of the z-axis into little subintervals of height dz. So that'll help us get our differential of volume. But before we get to that, let's again take our rectangle and turn it out in such a way that we can see it well. And to do that, we'll put it here. And just like when we were slicing perpendicular to the x-axis, our width is consistent. It's always going to be 4. Okay, but now we need to know this dimension here. And that dimension, if you think about bringing it down here, it is the x value that we are interested in to give us our, well, what we would usually call the height, I suppose, of our rectangles. Maybe in this case, length would be more appropriate, but we need to get that value right there. Okay, well, you could go to analytic geometry again. We also could use some more what you might call synthetic geometry, and just do some similar triangles here. So let's see. I wonder if I'll be able to change the color here. If so, that would be pretty slick. Let's try green. Okay, so you can see sort of here and here there are two triangles involved, and they are going to be similar triangles. So again, this is an alternative to using the slope-intercept form and so forth like we were doing before. So we got two triangles like this. Here is the x value we are interested in, and we're slicing at some height z. So this would be z here on the z-axis like I got it. So that height would be z. Okay, now we know that the whole height here is 2. And the whole length is 6. And that means that this little part in here, where am I going to squeeze this? How about right there? The length of the shorter length of the smaller triangle, that is going to be 2 minus z. Okay. And so from here, we can set up proportions of side lengths to get what x is. So looking at the smaller triangle, we got x over 2 minus z is equal to, so that's for the small triangle, and then corresponding sides of the larger triangle, we'd have 6 over 2. Now, of course, we know 6 over 2 is just 3. And then multiplying the denominator over, we would get that x equals 3 times 2 minus z. And you could distribute that, but I don't really see a need to. And so that is our height here, or our length of the rectangle, let's call it. 3 times 2 minus z. Okay, and then from here we can go to area and then to our differential of volume. Let's just jump right to differential volume right away. And so in this case, it is going to be area. So we got a rectangle. Remember, this is our shape over here. Okay, so it's going to be 4, which is that width, times the length is 3 times 2 minus z. And then remember that our height of the slab this time is going to be dz. Okay, again, slicing perpendicular to the z-axis this time, and that means we're going to integrate with respect to z. And so our overall volume is going to be the integral. And let's see, we can see here that along the z-axis, the extent of our solid is from 0 to 2. So we'll integrate from 0 to 2. 4 times 3 is 12. 2 minus z dz. Okay, anti-differentiating. You know that 12 we can just pull out. And then we're going to have 2z minus z squared over 2. And we want to evaluate that at 0 and 2. All right, so evaluating. Let's see. Maybe put this down here if it'll fit. We got the 12 still. That's going to stick outside. And then we got 2 times 2, which we know is 4, minus 2 squared. That's also 4, and then over 2. And then evaluation at 0, as it has been, will still be 0 in this case. And so we've got 12 times 4 minus 2, which is 12 times 2, which is, happily, what a relief, we again get 24 for the volume of this wedge. All right, so the volume's 24, no matter which way you slice it. We've been able to do this one 3 ways. But it kind of gives you some insights into, okay, how should I slice, and what kinds of slices might I get with slicing it a particular way. In this case, all 3 ways gave us familiar shapes that we know how to find the areas of. That's really the key that you're looking for, is can I give a formula for the areas of these slices, and then from there it's an easy step to differential volume, and then you just need to integrate. Okay, so I hope you enjoyed slicing this solid 3 different ways and getting the same volume every way, and we'll see you again soon.